Hey, can you hear me? So let's start. I'm very excited being here. First time in Poland for me. My flight was delayed, so I went to sleep at 2:30 at night. So if I'm talking nonsense, it's because I'm always talking nonsense. So, about me. I've started developing software since I was 13 years old. My first computer was Commodore 64. It's 64 kilobytes, meaning that it didn't have much of memory management techniques. Everything was very easy. I've been in my career a software developer, an architect, an engineering manager, and have done a lot of different roles and things. But part of my career, I have been an independent consultant that was focusing on performance problems. Part of them was solving garbage collection issues for my customers. I'm also a Java champion and one of the organizers of the Israeli Java community, Java IL. We're going to have our first conference in November, so if you happen to be on the 21st of November in Israel, you're welcome to join. I am a proud father of 2 daughters who are already adults. I had a joke about having adolescent daughters, but they are over that, so I cannot use it. But I do have a dog named Mushu after the character from the Mulan movie, the little dragon, the one that was in the first movie, not the second one that they ruined. And in the last 6 years, I've been working in a company named Next Insurance. It is modernizing the small businesses insurance in the US. And I was starting there as the first developer and building together with others than engineering. I'm now VP of engineering in Next Insurance. And the company grew from me, one developer, to over 200 developers. Over 150 backend developers working in Kotlin. I have talks about how we develop microservices in Kotlin, but this is not what we're going to do today. What we're going to talk today is about the birth and death of objects. And it is a very complex and frightening topic for a lot of developers. Think that as we are so afraid of that, we are ignoring it totally, and I would like you to come out of this talk less afraid and less ignoring, okay? I don't consider myself as a true expert of garbage collection, rather a garbage collection enthusiast. I've been seeing every talk about garbage collection in the last 13 years, maybe even more than once, talk with all the people that are working on garbage collection, but I haven't been involved in active development of garbage collectors, so I don't consider myself as a true expert. A lot of the talks that are available are trying to give a lot of theoretical knowledge and address very complex problems. This is not the main goal of this talk. I want to address mainstream applications with web app latency. Stopping the world for a few hundred milliseconds now and then is not a disaster for those applications. There are use cases like HPC and high frequency trading and huge heaps that are different things. And but for the main small microservices that we have out there, this is not a tragedy, even if the application stops from time to time. And I want to focus on how to monitor and tune your JVM, and not how to get to no allocation and all the other things that very advanced developers are doing. So we're going to delve into memory management terminology, discuss GC building blocks, because we need to have to be on the same page and understand the basics of that. Then I'm going to give a short introduction to all the garbage collection that we have on the OpenJDK JVM, and discuss monitoring technique and way to understand how the GC is performing and working. So this is a snippet from Stack Overflow about plans for Go 1.0, 1.4 garbage collector. And it says, hybrid stop the word concurrent collector, stop the word path limited to 10 millisecond deadline, CPU core dedicated to running concurrent collector, tricolor mark and sweep algorithm, non-general and compacting, fully precise. Great, no one left the room yet, so that's a good indication. We try to get to the end of the talk by you understanding what the hell they're talking about. So our application has memory. There is the code, which is memory that is usually not changing unless someone is hacking your code. But there is also the data, and the data consists of mainly three types of memory. There is the static data for global parameters, for static members of classes, etc. There is the stacks of threads, which are representing the frames of the threads and the working memory that the application is currently working on. And there is the big pile of garbage of objects in the heap that can be millions of objects, 10 of millions of objects, sometimes even billions of objects that are working and staying in the same place, pointing to each other and evolving and actually creating a lot of mess. When we handle memory, we have three participants in this game. The first one is the allocator, is the component that allocates memory and gives to the application wherever there needs additional object, additional memory, an array, something, give it to it. The second one is the collector, which is reclaiming memory and returning memory that you don't need anymore, so it can be reused. Otherwise, the memory will be depleted and we get an out of memory. And the third participant is you. You're called a mutator. You are allocating memory, but then you are changing references, you are changing the state of the objects, you are making a lot of mess. And together with the mess that your threads are doing, the allocator and the collector are trying to cope and do the best that they can do. So how do we allocate memory? There is the most low-level approach of C and C++ that you use new and malloc to create an object, delete and free to delete an object. But there are a lot of problems and challenges with that, and someone that has been developing in C and C++ for over 8 or 9 years, I don't miss it at all. You have dangling pointers, you can free the memory twice, you have memory leaks, you have fragmentation of the memory structures over time, which cause degradation of performance and even can create to some kind of out of memories at the end. Of course, there is the approach that Rust is taking now by borrowing memory and ownership and all of stuff. I will not get into it in this talk. Another approach is automatic reference counting that you use in Python, also in iOS, that what you're doing there is every object has the number of reference that incoming into it, and when this counter goes to 0, you just free it. So you have some kind of a mechanism that is accounting the number of reference to an object and reclaiming the memory when it goes down to 0. It works well unless you have cycles, and in order to break the cycles, you either do it brutally and breaking the cycles brutally, or you're adding garbage collector that will trace the objects and free the cycles as well. Reference counting has another problem, which I worth mentioning because this problem is related to garbage collectors as well, and there are a lot of mechanisms to avoid them. It relates to concurrency. If you have some kind of a counter on every object, if two threads are trying to modify this, it means that they are contending. And you need to synchronize and handle visibility and all of this stuff, meaning that reference counting is not very good for highly concurrent code and usually used on applications that are single-threaded, like Python. Okay. So that's the reason that most of the platforms, including Java and the JVM, are using what is called a tracing garbage collector. The tracing garbage collector is a mechanism that is actually taking the burden of collecting and restoring the memory back to the runtime and take the burden from you and solve all your problems. And life is amazing, it's a heaven, everything is working, and you don't need to think about it anymore unless. Have anyone in the room tried to take his daughter or his son to school and got stuck after a garbage collection truck in a single line street for an hour and she's late for a test? I did. Okay? The same things happen with garbage collection. If we don't understand what is going on there, very bad things can happen, and if we are not monitoring it properly, we will not even know that they happened. So there are basically 3 key performance indicators that we need to look at when we have a garbage collector installed in our system. And it doesn't matter which garbage collector you use, which runtime you use, you always need to put them in place. You need to be aware of that. Even if your garbage collector is doing poorly, believe me, it can do worse, okay? So what do you want to measure? We want to measure CPU and time overhead, meaning how much time is consumed by the garbage collector per unit of time. It can be CPU, but it can also be times that it is consuming the entire machine, for example, in pauses. And we don't want this to be very high, or at least we want to know how much it is. The second is the memory overhead. How much on top of the memory that you use, the garbage collector needs to have in addition in order to function properly. Okay? It includes internal data structures, but it also includes headroom that most of the garbage collectors need in order to work properly. Just to give an analogy, if you're trying to clean a room and the room is full with stuff, it will be very hard to clean it. Okay? You need some place to move things to clean and bring them back. So the same with garbage collectors. And the most notorious thing that you need to monitor is latency or pauses. Garbage collections can, from time to time, stop your application, and if you don't know what's happening there, it can be very long. It can reach seconds, in rare situations it can reach minutes, and you don't want to get outages of this kind. So let's go through some kind of terminology let's start with describing what is a heap. So we said that there is a static and stack objects that are pointing to our heap. Our heap is a very big memory region or several regions that has a lot of objects of it, and there are incoming references. In order to be able to use an object in the heap, you need to reference it. So the reference needs to come from outside. And the objects that are pointed from outside are called the root set. These are the objects that can be reached from outside. If there are no root sets in the heap, then you can't do anything. Everything is unreachable. Okay, so that's the root set, the start of everything. In addition to root set, we have what we call live set. The set of reachable objects, the object that we can get to them through the root set and can be used. This is the live set. The size of the live set is the size and the set of the memory that your application is currently using. It is always changing. It's not constant. It is increasing, decreasing, but to some extent there is a set of objects that are live, and this is something that you need to take into account when you're doing your calculations. Outside of the live set, there is what we call unreachable objects or garbage. These objects are on the heap. Actually, they don't know that they are dead, but no one can call them, and no one can get to them. And the only way that they will know that they are dead is when we reach chapter 9 of the series, okay? And then the garbage collection run and remove them from the heap. In addition to objects, there is also empty regions that we call the free list. And in the free list, there are places that you can allocate new objects. This is the places that you will take memory from in order to allocate new objects. So we have root set, live set, unreachable objects, and free list, okay? That's the main ingredients of the heap cake. Now let's talk about building blocks and algorithms of garbage collection. The first thing that we need to do is we need to understand what is the root set. And the process is called root scanning. Root scanning needs to go through all the threads and all the static members and generate the root set of the program so we can start the garbage collection process. In order to do that, we need to get to some kind of a safe point, to get to a point that it is safe to do so, because the threads are always working. They are doing things, they are calling method, they are returning, they are changing things. And you need to get to a situation that you are able to do it safely. This is not very easy. Most of the garbage collectors are doing it while stopping the applications. There are mechanisms that are very complex that enable us to do it without stopping the application fully and do it gradually. But basically, that's the first step of every garbage collection. The second phase, the second building block, is called marking. Marking starts from the root set and then traverses the heap and marks all the objects that are reachable. Okay? The amount of work that this step takes is proportional to the size of the live set. The more objects that you have, the longer the marking will take. If you don't have live objects, it will take 0 time, it will be very quick. Okay? This is called tracing or marking. Second algorithm that is involved is sweeping. Sweeping goes through the heap, scanning it, and looking on objects that are unreachable. Okay? And takes these unreachable objects and add them to free lists and generating space for the next application to run, okay? This process is called sweeping, and it creates a list of free lists, a linked list of free lists, and it has certain problems. The main problem of that is that it creates fragmentation. Over time, we'll get regions that are smaller and smaller, and that are maybe you have enough memory, but you will not be able to allocate a big object, okay? So sweeping is something that is not moving objects, but it's creating fragmentation of the heap over time. Another algorithm is called compact. Compact is doing something else. It's taking all the objects and compressing them to the beginning of the memory region that they are working on, let's say the heap. Okay? So they're actually moving objects, and this is very tragic. Because if you want to move an object and it has references someone is pointing to, then now nothing is pointing there and you're reaching an empty place, and the object that you're trying to reference has moved elsewhere, and it can create all the problems that is seen in C and C++. So being able to move safely an object requires fixing these pointers. And this can be done by either stopping the application and fixing everything, or do something that we call the memory barrier, either read or write memory barrier, that every time someone tries to read from a certain memory location, we check if we move the object. Okay, by certain techniques. There are the technique of garbage collector called Shenandoah, that's using Brooks pointer, and color pointer by ZGC and C4. And these mechanisms are enabling the JVM to move objects without losing the references, okay? But the memory barriers are slowing the application. They are slowing the application. It's not significant. They always say that it's 5 to 10%, but it is slowing the application down. So we have the compact and the mark and sweep, and there is another type of collector that is very important that is called the copy collector. The copy collector takes all the live objects and move them to another place. Okay, after the marking, we have the live set. We take all the live set and we move it to another place, and everything that is left there is considered garbage. It's like instead of cleaning your house every 2 years, just move to another house with the stuff you need. Okay, that's the approach of the copy collector, and it's very efficient because it is proportional to the live set. And in cases that the live set is very small, that we will see soon, it is something that can be very efficient. These compacting and copy collectors enable us to create contiguous regions, which makes the allocator work more efficient, which enables him to use a scheme that is called thread local bump allocation, which means that every thread gets a contiguous region of memory, and it can allocate sequentially over there, and thus using caches very efficiently. Okay, that's a very big win of all these compacting mechanisms, besides the fragmentation and out of memory, etc. Another thing that is very important to garbage collection is generational collectors. They are based on the weak generational hypothesis, which is some kind of a claim that is true for most applications, that objects that are allocated usually don't live very long. They serve a request, they serve a very short purpose, and then they die. Okay, so if object is young, most likely it will die, but if it is surviving for a very long time period, then probably it is part of the state of the application, and it should be continue living for a very long time. This creates an optimization of separation between the old and the new generation, and giving each one of them a different treatment. The old generation should be handled very infrequently, and it is very costly operation, and it will done as less as possible. While the new generation collection should be very frequently. They're using copy collectors, and most of the objects that are garbage, and they are very efficient. Okay, garbage collectors that are using generational mechanisms are more efficient in terms of overhead. They can collect more garbage with less resources and less overhead. Besides that, there are other properties of garbage collectors. The first property is either stop the word or concurrent. Stop the word garbage collectors stop the application, do the collection, and continue working. And while they are working, the application cannot work, and the longer the pause they are inducing, the more problematic the software will get into. So a collector can be STW or stop the word. It can be single-threaded, meaning that it can work with a single thread to collect. And it can be monolithic, meaning that it's collecting the entire heap at once. It can be also stop the word incremental, which means that it starts collecting, it can stop the collection, continue to run, and then continue the collection. And it can be parallel, meaning that several garbage collector threads can work together in order to do the work. Besides stop the word collector, there are concurrent collectors that are working together with the application. They are consuming resources from the machine, but they are not stopping the application, enabling it to continue to function. They can be single-threaded and they can be parallel. The problem with concurrent garbage collectors, at least with most of them, that they are not fully concurrent. There are steps that they do stop the application, and while they're trying to do so as infrequent as possible, it does happen from time to time. And it's important to remember what we are looking when we are monitoring these processes is to try to find the places and the times that it happened and try to minimize them and reduce this pause time as much as possible. One thing that's worth mentioning in the context of stop the word and concurrent collectors is when are we doing garbage collection? The point is that we want to delay garbage collection as much as possible. If possible, never, okay? But this is not possible, so we want to delay it as much as possible because the longer we wait, the higher possibility that object will die, the ability, we will do less work in order to finish our process. So for stop the word garbage collector, it's very easy. We do the garbage collection when the heap is depleted. We are done, we're stopping everything, we're cleaning as much as we can, we continue. For concurrent collector is not very clear, and what you're trying to do is to find the optimal point that you are taking it as late as possible without getting to a position that you will get out of memory before you finish the collection. This is called to lose the race. If you're losing the race, you cannot continue to do the collection concurrently. You either stop the threads, store them, or you throw an out of memory error. Worth mentioning that there are two kinds of garbage collector, conservative and precise. Precise know exactly which points in the memory are pointers. Conservative do not know. To be precise, you need help from the compiler. All the collectors in Java are precise, so it's not very important. Let's go over the list of garbage collectors that we have in Java, current JVM, JDK 17. We have the serial collector, which is precise compacting. It is regional, meaning that there is old and new generation. Sorry, it's not regional because it doesn't break I forgot a slide. Let me go back. Regional garbage collectors are collectors that are taking the heap and breaking them into pieces in order to do partial work every time and not handle with this entire heap at once. So serial collector is not regional, but it is generational. It has new and old. It is not concurrent, and it's not mostly concurrent. And we use it for small heaps and with very low CPU, maybe containers with one CPU, or maybe embedded devices, usually not in the common use case. Parallel collector is same as serial collector, but is going to work with several threads. It is stopping the word, taking all the power of the machine in order to garbage collect it, okay? It is very efficient. It's the collector with the highest throughput that we have. And the problem with that is latency. So if your application is not sensitive to latency, if you are doing some kind of batch processing or something that is not sensitive to it, use it. The default garbage collector at the moment is G1. It is regional. It is sort of concurrent. It's sort of mostly concurrent. It's not concurrent. And it is working quite well for most standard applications. We will see its limitation later on. I don't think that the future lies in G1. I think that the new garbage collectors that they are being developed for OpenJDK are going to replace them eventually, but they have some limitation at the moment. One of the garbage collectors that is developed today is called ZGC, and it is mostly concurrent with a pause time of up to 1 millisecond. The problem with this garbage collector is that it's not generational, meaning that if you have high allocation rates, you will need a lot of overhead in order to be able to cope with these allocation rates. Okay. Making it generational is work in progress, but it will take time. The second algorithm is developed by Red Hat and now by Amazon. It's called Shenandoah. It's also mostly concurrent with poses of up to 1 millisecond. It's also not generational, but I think that the work toward generational garbage collector is more advanced for this garbage collector. I hope it will be in production soon. And there is also the JVM of Azure that is called Zing. It has the C4 garbage collector, which is probably the most advanced garbage collector on the planet at the moment. And it has a lot of benefits, but it also comes with a cost because you need to pay for a JVM in this case. And it can be expensive for cases that it does not justify the extra cost. So for the rest of the time, I would like to get practical. So I said that we need to do monitoring for your JVM. What should we monitor? We should monitor the CPU and time overhead. We should monitor memory overhead, and we should monitor latency and poses. How do we do that? The best approach to do that at the moment is using garbage collection logs. I would like to ask you, who is having garbage collection logs open in production? Don't be shy.
We have dashboards.
Okay. If you don't have, please do. Okay, it's not creating a lot of overhead. It's very beneficial in order for you to understand what's going on with your application. You are blind without it. You don't know if the problems that you're seeing are coming from garbage collection. Maybe there are a lot of other problems in your application, and it's very easy to enable them. And when you enable them, every event of garbage collection is recorded into a log file. Okay? It's not a lot of data. Don't be afraid. And what you have in these log files is, first of all, description. Okay? It explains what the garbage collection was doing at the time that it was operating. It has a timestamp. When did it happen? It has how much memory did it clean. You can see that you have here 4,000 megabyte, which is 4 gigabyte. That's the size of the heap. And you started from 486 megabyte, and you cleaned to 130 megabytes. So that's the amount of memory that you released. And you also know how long it takes. Okay? With this data, you can do a lot of things. You can calculate the overhead of the garbage collection. How much of the resources of the machine is going towards the garbage collection. You can know the frequency. You can know the post time, the distribution of the post time. How many times it exceeded the limit that you were willing to give. If you say that I don't want more than 200 millisecond post time, because that's a promise of G1, does it really happen? I can assure you not. G1 does not meet his goal in post time. I've never seen him does that, okay? And you can also calculate the allocation rate, because if you know how much you free, you can also understand how much you allocate. So a lot of valuable data. The problem is that, first of all, the creators of these logs have made a wonderful job in creating a format that is, on one hand, not human readable, on the other hand, not machine readable, and it's quite hard to understand what's going on there. The basic stuff is easy, the more advanced stuff is relatively hard, but you can get a sense of what is going on in your system, especially if you're trying to understand, for example, at a certain point in time, why my application was not responsive. Is it related to GC? You can know that from garbage collection log. Otherwise, you don't know what happened. There are tools that are analyzing these these logs. One of them is called GCViewer. It's an open source project. You can download, build, and feed the garbage collection log into it and see very nice graphs of saw chains and memory. But you can get from this tool some very important information. The first thing is how much memory was left after a full GC. That's the live set of your application, okay? Live set is changing all the time, but if you have a lot of such measurement, you can try to start to understand how much memory your software is consuming usually, okay? Second thing that you can understand from that is the throughput, okay? You can understand how much of the resources are going to garbage collection. If it's over 5%, probably you have a problem, okay? And the last thing are the pauses. You can understand from that how many pauses are, what are the biggest, what is the distribution of that, etc., okay? So remember, time overhead and CPU overhead, memory overhead, and pauses are things that you must know on every production application that you have, that you care of. Another tool that you can find online is called GC Easy. It can show you the duration of garbage collection and also the pauses, how they distribute, and it gives a very nice graph to understand what's going on, okay? Another thing that is used and can be very helpful are JMX. There is a JMX called Java Lang Garbage Collector. It is not my favorite because it can lead you to incorrect decisions, but it still can give you a hunch of what's going on there. You can use a tool that is called Visual GC that is based on these mechanisms, that you can see how the memory is going up and down and how things are looking into. Can use directly on the MBeans or emission control, other tools that can be very helpful to understand things. And the last mechanism that I want to show is called Hiccup. It's based on work that Gil Tana did that is called JHiccup. Basically, creating a thread that wakes up every certain period of time and asks how much time had passed. If the time that had passed is not exactly how much it went to sleep, it means that it had a pause. The pauses can relate to garbage collection, but they can relate to other things, okay? Especially if they're under 1 millisecond, they can come from the operating system, from the fact that you're running on a virtual machine, etc. Things you do have pauses from time to time that are not related to garbage collection, but from these mechanisms you can understand if the pauses are big, most likely they're coming from garbage collection. In order to estimate live set, that's the size of the memory that the process is using, usually it's not good enough to look on the garbage collection logs and the heap graphs, etc., because the garbage collector not always releasing all the memory that it can. So in order to understand how much memory the system is using at the moment, you will probably need to run system GC either by heap dump or directly in order to understand what's going now, okay? In that case, it will release everything that it can. It can take time, it has implication, but it will give you indication of how big is the live set of your application. And the live set of the application can consist of two things. The first thing is the long lasting. For example, if you have a cache, it may change a bit, but basically it consumes a set of memory, and the bigger it is, the more complex it to handle, and sometimes it's worth optimizing these caches and making them to consume less memory. But there is also the working memory. Every request that you're doing is consuming memory, and you want to try to understand and estimate them in order to understand how much memory your application is generating for a certain period of time, and where does it come from, okay? Common problems that we have in garbage collection. First of all, overhead. If you have a garbage collection that doesn't have enough memory, it will kick in too frequently. It will consume too much resources. And as a result, your application will not be able to be effective and up to speed. Usually the solution to that is to increase the memory. But if you're not using a generational garbage collector, you might be using a generational garbage collector instead. That will also improve your GC overhead and improve your throughput. And of course, sometimes moving to the latest JVM can solve these problems because the garbage collectors are advancing all the time, all of them. Latency. You need to be sincere with yourself how much latency you can tolerate. We are very annoyed by 200 millisecond latency, but I can say that for my use case and our company, it doesn't really matter. Okay, even 500 millisecond latency and pause time is not that dramatic because up until now, people used to do insurance with an insurance agent, and the pause time there was a few days until you get an insurance policy. Okay, so everything is an improvement, and you work with third parties that are having response time that are awful, maybe 60 seconds, etc., and you cannot control that. So this half a second is not very important, but there are applications that is critical, and there are applications that is important. The application that it has dollar impact. So it depends what you really need. If you need something that is low latency, you will have to pay the price, either to pay for Azul, for the great JVM and garbage collector, or pay with additional memory. Sometimes you will need like twice the amount of memory, and that costs for your operation, okay? But it's definitely something that you need to understand and decide what to do. And of course, as we said, being able to cope with a high allocation rate of a garbage collector can be handled by adding more memory. But if you take down the memory, you might get lower throughput, but the system will still work. It is something that you can also trade or move to a generational garbage collector that might be with more pauses, but has less memory overhead. For example, ZGC does not support compressed pointers. Compressed oops means that its memory is 30% higher than, for example, G1 that support compressed oops, and Shenandoah that support compressed oops. Another thing and problem that we have been encountering is caused by fragmentation. We said that copy collectors and compacting collectors cannot have fragmentation. We do have fragmentation when it comes to humongous objects. G1 does not cope well with humongous objects. If you allocate big objects, you can get to a situation that you get out of memory, even though your memory is almost empty. I have an example that I allocate memory, free half of it, and try to allocate another large array and get out of memory. That's why you need to make sure that you don't allocate a lot of humongous objects. If you do so, probably better move to ZGC, because ZGC is less sensitive to this kind of problems. I will skip that. The last slide is some kind of a questionnaire that I urge any one of you to fill in when you go back home, which is what is the size of the process heap, what is the GC overhead, what is the max pause time, what is the number of collections that were pause times exceeded my goal, what is the live set size, what is the allocation rate. If you don't know these numbers for all of your services that are running in production, you're probably missing something. You might be very surprised by the results of this little exercise. Further reading, there is a book this thick about garbage collectors if you want to read, and 2 books about Java performance. Of course, all the talks of the people that are developing ZGC, Gil Tene from Azure developing C4, and Kevin Nielsen from Amazon, who's currently working on Shenandoah GC. I highly recommend to watch them. So, just in time, thank you for your time and good luck with your GC poses.
Just one